All right, folks, welcome back. We're going to continue on our little discussion on two-dimensional forces. Wanted to split this up for you. So last video lesson we looked at when things were in equilibrium, or what are called statics, when everything was balanced. So we're going to look at today is just when things are unbalanced. So again, unbalanced forces has to pertain to Newton's second law of motion that states that when you look at the forces up, down, left, and right, that if they're unbalanced, it's going to cause that object to accelerate. So we've seen kind of these diagrams before, but now we're going to make use of two-dimensional forces. So you'll see here that I have an applied force being, applied at an angle of 45 degrees, and that's equal to 80 newtons. We have the force of gravity, which is pulling downward. We have a surface, obviously, here. So we have our normal force pushing up, and then obviously with the motion object potentially moving, that we have the force of friction going on here. So just a couple things as we go through this, just understand we had some relationships we talked about with forces. For example, we had the force of gravity, which is related to the mass of the object. We had the force of friction. That was that coefficient times the normal force. So we're going to make use of some of those things here. But again, what we're going to use as well is our idea of forces acting in two dimensions. So you'll see this 80 Newton force acting at an angle of 45 degrees. So any force that's acting at an angle, again, is going to have components. So this will have a component to the right and a component upward. All right, so to understand this, again, what we're going to do is we're going to look at the forces being unbalanced. So when we break this force down into components, know that we have a rightward component that's going to be working with friction. We have gravity in our normal force, but where this is going to be different now is that because this force is being applied at an angle, not only do we have our normal force upward, but we have our component of this applied force that's also upward. So where this is going to change is that normally when we did diagrams like this, we always said that the force of gravity was balanced out by the normal force, especially this being a level surface. But now in this case, because there's an upward component, we can no longer say that. Okay, the upward component is going to take away from that normal force. We do know that the object has a mass of 20 kilograms, so I also do know that the force of gravity multiplying this by 10 should be about 200 newtons. Okay, now normally, no pun intended, we would say the normal force is 200 newtons, but again, because this upward component is going to take away from that. So what I should see upward is that I have my normal force pointing upward. Okay, so I'll write this as Fn. I have my upward component of that applied force upward, and then I also have the force of gravity, which is 200 newtons. So essentially what happens is the normal force and the upward component have to both combine equal 200 newtons. So this is slightly different than what we did before. So to find this upward component, what we're going to have to use is our trig function. So if I know the overall force is 80 newtons and it's 45 degrees, what I'm going to use here to find this vertical component is I'm going to use the sine. And we're also going to might as well just do cosine to find that horizontal component. So real quick, just going to solve for those two things. So again, my vertical component and my horizontal component. So doing so, again, 45 degree angle means that they're both going to be the same, the horizontal and vertical component. But I'd get about 57 newtons here. So again, that was using the sine. And then the horizontal component, I'm going to get the same thing. Again, using the cosine, I'm going to get 57 newtons. So it didn't really show the work there, but assuming at this point you guys are pretty good with finding those components. So therefore, putting this together then, in the upward direction, we're going to have my y component that the applied force is 57 newtons. I know gravity is 200 newtons, so that means that the normal force is going to be equal to the amount that would get me up to 200 newtons. So again, up and down, those forces should balance out. So 57 plus certain value is going to give me 200 newtons. So I know that the normal force in this case is going to have to be 143 newtons. So again, that's a little bit different because it's not entirely 200 newtons that's balancing out with gravity, but my normal force is simply going to be 143. That means the surface, because I'm partly pulling it upward, the surface doesn't have to push as hard up on the object. Now I am realizing that with this problem, I did forget to give you a piece of information. So let's just say that my coefficient of friction was 0.2. Okay, that was supposed to be part of the problem. That's my fault. So again, if the coefficient of friction is 0.2, we talked about that. The relationship between friction is that friction is always a percentage of, and I kind of use this in a different way to get you to understand, but I always said that it was always a percentage of the weight. But the force of friction is always a percentage of the normal force. So think of if my coefficient of friction, of which I give you, is 0.2, That means that 20% of this normal force, 143, is going to go to friction. So in terms of my left and right forces, if I want to find the force of friction, all I got to do is take that coefficient of 0.2 and multiply it by the normal force, 143. By doing so, that's going to give me a force of friction equal to 28.6, all rounded up to 29 newtons. So again, it's a percentage of the normal force. So my force of friction is 29 newtons. So basing on this, okay, we can see that we have the rightward component, which is 57 newtons. And I see that I have the force of friction acting left, which is 29 newtons. So notice that these forces are unbalanced. And it's then going to create, based on them being unbalanced, it's going to create a net force that's going to be equal to the difference between those two things, which in this case is going to give me about 28 newtons. So there's going to be 28 newtons of leftover force. Now again, according to Newton's second law, that 28 newtons is going to cause that mass to accelerate, and we could actually go ahead and find this acceleration if we wanted to, okay? But that would be the next connection we're going to make. But in this case, just want to show you how things would work two-dimensionally with unbalanced forces. Okay, so we got the same thing going on here with example B. I'm going to slide this over so I have a little bit more real estate to play with. But similar diagram here. I have the same force of 80 newtons, now acting at a 30-degree angle. Notice I give you friction. So let's go ahead and try and solve for this one. So again, first thing I want to understand is that when I have a two-dimensional force, it has a component going to the right, and it also has a component going upward. So what we're going to do is look at this in separate directions. So up and down, we have our normal force pointing up. We have gravity pointing down. My applied force has a component going upward. So up and down, here's what we have. We have that component going upward. We have our normal force going upward and gravity. So let me just label these quick. And I'll just write this as Fy. That's the y component. So then know that, again, just like in the last problem, those things have to be balanced. So if I know that the thing is 20 kilograms, shown in the diagram, then I know right away the force of gravity is going to be 200 newtons by multiplying that by 10. What I then have to do again is I'm going to have to go ahead and find these components. So I'm going to have to use my sine to find the vertical component, cosine to find the horizontal component. When I do that, I'm going to get a vertical component equal to 40 newtons and a horizontal component of about 69 newtons. Okay, so if my vertical component here is going to be 40 newtons, oops, sorry about that. The normal force, in order to get up to 200, then my normal force would have to equal 160 newtons. So again, the normal force is going to be the difference between that vertical component and gravity. So again, that's going to equal 160 newtons. All right, now again, looking at, oops, I'll fill that out too for 200 newtons. Again, looking at the balance or unbalance of forces, it appears, with normal force, y component, and gravity, those things balance up and down. Right and left, I see 69 newtons to the right, 40 newtons to the left. So again, if I compare right versus left, I would have 69 to the right. I would have 40 newtons due to friction to the left. Therefore, I know that there is going to be a net force and unbalance of 29 newtons that's pointing to the right. And that 29 newtons will cause that object, whoopsie daisies, I don't know what I was writing there. It's going to cause that object to accelerate based on Newton's second law. And again, we can apply that idea. In this case, we're not going to. But in here, we did do some problems where we solved for the coefficient. So now, if the force of friction is 40 newtons and my normal force is 160, the coefficient of friction is going to be the ratio of how much friction there is to how much normal force there is. So I would have 40 newtons divided by 160 newtons. And obviously, that's going to give me a coefficient equal to 0.25, so 1/4. Okay? But again, it's just applying the ideas we talked about with Newton's second law. It's just, again, because of forces acting in two dimensions, just a little extra work. And adding into these components, again, we normally looked at an applied force just strictly going to the right. Essentially, what's happening here, the only thing that's changing is that by having this force go at an angle, there is now a vertical component. And that vertical component takes away from the normal force. And if it takes away from the normal force, that makes friction a lot less than what it was before. Okay, so that's kind of the main thing that's going on in your main difference. But again, we're just looking at how two-dimensional forces are going to affect things based on it being unbalanced. I'm going to do one more example in C, and then I'm going to have you guys do D on your own. So in C, again, we got the same kind of thing. The only difference here is working backwards. I have my applied force acting at an angle. Holy strawberries, it's going up and left instead of up and right. Not a big deal there. But know here that I don't give you the applied force, so we're going to have to solve for that. I do give you the normal force. I do give you the mass, certain things, so we're going to have to find the information based off of this. So right away, I know that my force of gravity for the mass is 10. My force of gravity is going to have to be 100, okay? Now, knowing that my force of gravity is 100 and my normal force is 80, again, any sort of force that's acting at an angle, my applied force is going to have components. So there's going to be a component to the left and a component acting upward. So upward, I have that vertical component. I have the normal force, which is 80 newtons. I have gravity downward, which is 100 newtons. So what does this blue arrow need to equal? Well, the blue arrow needs to equal 20 newtons in order for me to have that 100 newtons of force. So just like previously stated, my normal force is going to be a little bit less because now I have a vertical component here of 20 newtons that's taking away from that normal force, but still balancing out with gravity, which is 100 newtons. Now, the only difference here is that I don't have information in regards to my left and right forces, but I am able to solve for this using my trig ratios. Now, how this is different, and I'll draw this over to the side, is that I now know my vertical component is 20. I do not know my horizontal component, and I do not know the resultant vector, my applied force, that's unknown, but I do give you guys the angle of 30 degrees. So kind of like we did in our last little video lesson with equilibrium, in this case we're going to have to use our trig functions in reverse. My goal is to solve for this overall component, this resultant, sorry, not the component, but the resultant vector. I want to find this actual applied force. To do that, I know that the side that we're given right now, the component, is the vertical side. So to solve for that, I would use sine. I would say, okay, the sine of 30 would equal that vertical component of 20 newtons compared to that applied force. So let's write this as FAPP. So sine of 30, again, when you punch that into a calculator, is going to give you 0.5 or a half. So I want to know 20 divided by what number, I'll just write this as F, would give me 0.5. So I know just based off of that my applied force should equal 40 newtons. So right there I can automatically determine my applied force by using my trig ratios. Now the only thing that's not given here is obviously we got to find the force of friction. So again, the force of friction is going to be, based on our equation, is going to be a percentage of the normal force. So it's always dependent on the normal force, but then this mu value, that coefficient of friction, is like a percent. So again, I forgot to give it to you in this problem, forgot to jot it down. But let's just say in this case that the percent of friction was 30%, so 0.3. To find the force of friction, I'm going to take that 0.3 and multiply it by the normal force, which in this case is 80 newtons, and that's going to tell me how much friction there is. And that would give me, in this case, 24 newtons of friction. So I know that my force of friction is 24 newtons. Now, just to show you again the unbalance of forces, friction is a rightward force in this case. So I'm going to go ahead and now, since I've already solved for the upward component and the resultant vector, I'm going to solve for the horizontal component too. Now, I got some options to do this. Since I know, if you think of this as a right triangle, since I know this is 40, I can use Pythagorean Theorem. I can use the cosine of 30. I got different options to try and figure out what that horizontal component is. So depending on what you want to do, you should get a horizontal component of about 35 newtons. Okay, I think the easiest way, and the way that I did, is by using Pythagorean Theorem, where you would say, okay, if this is the resultant, it'd be 40 squared. The only difference here is that it'd be minus 20 squared, and we would use that to try and find the horizontal component. But if I know that my horizontal component is 35 newtons, I can then compare that to friction, and obviously 35 is going to be 11 newtons bigger than the force of friction, so we're going to see that as unbalanced forces. So again, I could use that to figure out the acceleration of that object if I wanted to. All right, what I'd like for you guys to do right now is I want you to try, I know there's a lot going on, I'm kind of talking fast, but I want you to try example D on your own. So example D, your goal is to solve for the unknown information. The difference here is that in this problem, it is a frictionless surface, so there's no friction. So if it helps, that coefficient of friction is going to equal 0. Your goal is to fill out the rest of the information. So what would be your force of gravity? What's the applied force? normal force. You're given here, instead of friction, there's an applied force acting to the right, and then there's a separate applied force of 100 newtons acting at an angle of 45 degrees. Okay, so I want you to find here the remaining forces and then to show that things are unbalanced. So pause the video, give this one a shot. All right, so go ahead and check it out. So what I did here is I found, again, my two components. So both, because it's 45 degrees, both be 71 newtons. So vertically, I have 100 newtons downward for gravity. I have 71 up for the vertical component, So therefore, my normal force is 29 newtons. All right. Right and left, I have the applied force of 50 newtons. I'm going to compare that to the leftward or horizontal component of that other applied force, so which is also 71 newtons. So showing again unbalanced forces, there's a net force of 21 newtons acting to the left. And just for S's and G's here, I then applied Newton's second law that if this is my net force, and knowing the mass, I know then it would accelerate at 2.1 meters per second every second. So a lot of meat and potatoes going on here in this little lesson. It's just using these two-dimensional forces to analyze things of unbalanced forces that we did back in Chapter 2. If you have any questions, jot them down. A lot of information. We'll see you guys in class.